Do you remember when we did this? You ever wonder how long that thing is? How long is this path if I had to walk it? How long would it be? Well, we have tools to figure that out, and here's how it goes. So first of all, in general, let's say I have a parametric curve determined by x of t, y of t. All right, so here's a point, and here's a point, and this is x of t0, y of t0, and this is x of t1, y of t1. All right, so basically time has gone by, and this particle has moved from here over to here. All right, we want to know how far that particle has traveled. All right, so what we can do is approximate it using differentials and then use the limit to make our approximation exact. So that's basically what we do. So we're going to say, all right, if I go from this point to this point, what do I do in Cartesian coordinates? I go a distance delta y and a distance delta x. And then I can say that what I'm really interested in is delta s. How far did I actually go? So it should be pretty obvious how I'm going to figure that out. It's going to be using Pythagoras theorem. So we can say that delta s squared equals delta y squared plus delta x squared. I don't know why I put the y first. I really didn't want to, but I did anyway. So delta s is equal to the square root of, let's put the x first, delta x squared plus delta y squared. All right, now, can I get a handle on this based on the functions x and y that determine this parametric function? In our example case, it's these two functions. All right, but I want to start with a general case. We used any functions at all. So what we want to be aware of is that you can use essentially like the Euler approximation method. You can say that delta x is approximately equal to the rate of change of x with respect to t times the change in time. Okay, so dx dt is essentially the velocity in the x direction, dy dt is the velocity in the y direction. So if I want to know the change in distance, I just multiply the rate at this time times the amount of time that elapsed. And of course, we know from Euler's experience method that can get pretty far off, but we're going to use a limit to make sure that it doesn't get off at all. All right, so then similarly, delta y is equal to dy dt. Delta t, essentially the rate at which the particle is moving in the y direction, that's dy dt, times the amount of time that elapses, delta t. All right, so then I can say in this equation that delta s equals the square root of dx dt delta x squared, because the delta x is being replaced by dx dt delta t, plus, for the delta y, we're going to put this expression, so dy dt delta t. This needs to be a delta t right there, delta t squared. That's important, delta t. So delta t squared. All right, that's what delta s is. So that's what this delta is. And these are really approximate at this point, right? Because this statement is exact, but this one, I've replaced dx dt delta t for delta x. That's an approximation. These are both approximations. All right, so this remains an approximation. All right, and then I'm going to factor out the delta t and say delta s is approximately equal to dx dt squared plus dy dt squared. And then if we factor out the delta t squared under the square root, so I have this factor of delta t squared, and then I factor it out of the square root, so I'm just going to have delta t. All right, so that's approximation. But when I take the limit as delta t approaches 0, so then, you can go back and like really go down the rabbit hole of exactly how what I'm about to write works. It essentially comes from the sandwich theorem, but we can write it like this now. ds is equal to the square root of dx dt squared plus dy dt squared dt. So what we mean by the limit as delta t approaches 0, we're really saying ds dt equals this. And that's a rigorous equal. It's no longer an approximation. And then we can just integrate both sides with respect to t. So well, actually, we're integrating this side with respect to s, this side with respect to t. So the integral ds is equal to the integral of square root of dx dt squared plus dy dt squared dt. And that's basically all we need to know. And then we can say, all right, so if I have a specific arc length between two values, then the s, the distance of the arc length between those two t values, is going to be the integral from a to b. All right, so t0 and t1 these are really like delta t apart. So the a and the b here are really more like the 0 and the 2 pi, right? So integral from a to b of the square root of dx dt squared, and it's nice to put the parentheses, but you don't have to. A lot of people don't. Plus dy dt squared dt, and then here's a general formula for the arc length of a parametric curve. Arc length of parametric curve, which we will now use to find the length of this shape and see why the thing we come up with makes sense.